This video is about sigma notation and evaluating finite sums. So in the last video, we were talking about antiderivatives. Now we're going to pivot and talk about finding the area of a region in the plane, but we actually don't get to that in this video. In this video, we're preparing to get to a point where we can talk about finding the area of a region in a plane using finite sums. And it might seem that finding this area of a region in a plane is completely unrelated to finding an antiderivative, but it turns out that they are intimately related through something called the fundamental theorem of calculus, which we're going to get to later. But for right now, we're going to focus on this idea of sigma notation and evaluating finite sums, because it's going to prepare us to find area of a region in the plane. And then that will be eventually tied to the idea of anti-differentiation and integration in just a little bit. So it's going in that direction. We're getting there. Okay, so this video is about sigma notation. We'll talk about what the terms are in sigma notation. We'll define the index of the summation, and we'll talk about the ith term of the sum and the lower and upper bounds of summation. We'll look at some properties of summation and summation formulas, and then we will evaluate a sum for several values of n. Let's say we want to add some numbers together. One way that we can represent that is with this notation here. A sub 1 is the first number on our list. And then we want to add a sub 2 and add a sub 3 and add a sub 4 and keep going until we get to the nth term. Now if n is large, I mean even if n is say 4 or more, this is a lot to write. We'd like to have a compact notation for expressing this same thing. One compact notation that we have for this is called sigma notation. If it sounds like Greek, that's because it is. This is a Greek letter sigma. Just means to add. This expression in front of the sigma is a sub I. That is called the ith term of the sum. The number below the sigma is typically denoted like that. I equals 1, that tells you where to start counting, and the number above the summation sign, that sigma sign, is an n that tells you where to stop counting. So this is just shorthand for this. And again, this is called sigma notation, because that is the Greek letter sigma. Sometimes people will just call this summation notation. It's just shorthand for this sum. These numbers, a sub 1 through a sub n, are called the terms of the summation. This letter I is sort of a dummy variable. It's just a symbol, it's a placeholder. We're going to substitute I equals 1, I equals 2, I equals 3, and we're going to stop when I equals n. This is called the index of the summation. A sub I right here, well, that's the ith term of the summation. If I is 10, that's the 10th term, it's a sub 10. If I is 15, that's the 15th term. If I is 4, it's the 4th term. It doesn't really work for 3, it's not the 3rd term. But you get the idea. that subscript is a placeholder for which term it is on our list, provided that we're starting with I equals 1. So this is called the ith term of the summation. And this number here is called the upper bound of the summation. It's above the sigma. And this number here at the bottom is called the lower bound of the summation. A lot of labels on that little picture. That's the ith term, the upper bound, the lower bound, the index of the summation. And when we expand it, a sub 1 through a sub n are called the terms of the summation. Again, this is just shorthand for a sum. Now, this a sub I just is a stand-in for a number. So here's an example. I have the sum as k goes from 3 to n, or excuse me, 3 to 9 of k squared plus 1. That can be expanded in this way. Well, this index of the summation is k. Oops. Let's identify the lower bound and the upper bound. The lower bound of the summation is 3. The upper bound of the summation is 9. And the ith term, well, in this case, it's the kth term because our index is k and not I. The kth term is that k squared plus 1. So this we could denote by a sub k. And all of this is a shorthand for a sum of several terms. So let's expand this and figure out what this is equal to. To find the first term, I just look at a sub k and I substitute k equals 3. This is my a sub 3. And then I add what I get when I increase that index by 1. So when k equals 3, we get this. When k equals 4, we'll call that a sub 4. We'll get that. We're going to keep going until we get to 9. So we have k equals 3, we substitute, and then we add. Then we let k equal 4, we substitute, and then we add. Then we let k equal 5, we substitute, and then we add. That's a sub 5. Then we let k equal 6, we substitute, and then we add. We keep going until we get to 9. So then we'll let k equal 7, substitute and add. Let k equal 8. Substitute and add. And then k equals 9. So we substitute and add. That's a sub 9. And then we stop because the upper bound of the summation was 9. So k equals 3, that tells you where to start. So you substitute in k equals 3, you get that. And then you add, and you keep increasing this index by 1. So you let k equal 3, 4, 5, 6, 7, 8, and 9. And every time you let that k increase by 1, you substitute and add, substitute and add, substitute and add, until you get to the last value of the index. You substitute and add, and then you stop. or you substitute, you don't add actually after that last one. You substitute and then you stop because it says stop there at k equals 9. So this summation is shorthand for this. You can see why a person wouldn't want to write this when you could just as easily write this and mean exactly the same thing. Now, if I want to find the value of this summation, then I actually have to figure out what a sub 3 through a sub 9 are. So a sub 3, that's 3 squared plus 1, that's 10. Then we've got 4 squared plus 1, that's 16 plus 1 is 17. 5 squared plus 1, that's 25 plus 1 is 26. Then we've got 36 plus 1, it's 37. 49 plus 1, oops, that's 50. 64 plus 1 is 65. And then the last one is 81 plus 1, that's 82. So this is a sub 3, a sub 4, a sub 5, a sub 6, a sub 7, a sub 8, and a sub 9. And we add them all together, and that gives us the sum of that original expression. This is the value of this. Then if I use a calculator for the arithmetic, so I do 10 plus 20, or 17 plus 26 plus 35 plus 50, all the way to the plus 65 plus 82. I do all of that and I hit enter. I get 287. So this is just shorthand for 287. You can see how you would prefer to write it this way rather than writing it in this expanded form. But that's all that represents. You just expand it, actually simplify each of those terms, and then add them together to get the value of that summation. Let's do one more like that. Say somebody asks you to find the sum of this summation. We have the sum as I goes from 1 to 4 of 1 over 2 times I. Well, the index of the summation this time is I. The lower bound is 1, that's where we start counting. The upper bound is 4, that's where we stop. And then the ith term is 1 over 2i. So a sub I is represented by 1 over 2 times I. It's like a function, but we're using slightly different notation for that function. And instead of writing f of x, we're writing a sub I. And we replace that I with different values, different integers. So this is the ith term of the summation. Okay, if I want to write this in expanded form, I just substitute in the first value of I here. So I get 1 over 2 times the first value of I, which is 1, and then we add. Then substitute in the next value of I. The I increases by 1 every time. So I was 1, now I is going to be 2. Substitute and add. Then I will be 3. So we substitute and add. Then I is 4. We substitute. If this index wasn't 4, we would keep going, but the upper bound of the summation is 4, so we stop. So this is the expanded form of this. And if I want to simplify, I can. This is 1/2 plus 1/4 plus 1/6 plus 1 over 8. And we could get a common denominator if we wanted to, but I think I'll use my calculator for this as well. So I've got 1/2 plus 1 over 4 plus 1 over 6 plus 1 over 8 and we get 25 over 24. If you're saying this is way too easy, you're right, the arithmetic is easy, but what our goal is here is to make sure you understand what this form means. So if you can take this and you can write it like this, and then you can simplify, then you truly understand what this form means and what this form means. And that's what we're trying to get at here. Okay, now sometimes someone will give you a sum in sigma notation, and then they'll ask you to expand the sum and then find the sum, like we just did. Let's do one more. Last one. Let's say somebody says, find the sum as I goes from 1 to n, or 1 to 3 of 4. Now, if you're saying to yourself, there is no I in that expression, you're absolutely right. And that's okay. We can still expand this. The index of the summation is I. The lower bound of the summation is that first value of I, so that's 1. The upper bound is 3. And A sub I, that's the ith term in the summation, is 4. Notice that it does not explicitly depend on I. But when I expand this, I know I have to keep adding from I equals 1 to I equals 3. So first I would substitute in I equals 1. I'd call that A sub 1, but there's nothing to substitute, so I get 4. And then I add. When I equals 2, I would substitute that, but there's nothing to substitute. Or there is something to substitute, but there's nothing to substitute into, right? So when I equals 2, we get A sub 2, which is also 4. When I equals 3, guess what? We still get 4. But we stop here because it says sum as I goes from 1 to 3. So we end up with 4 plus 4 plus 4. So we just get 12. So if there's no I here explicitly, that doesn't mean that this can't be expanded. It can. You're just adding that constant to itself that many times. You have to substitute I equals 1 here, and this represents A sub 1. And then this is A sub 2, and this is A sub 3, where A sub I is always equal to 4. You add those together and then simplify. Okay. Now sometimes we can go the other way with sigma notation. Someone might ask you to use sigma notation to write a sum. Let's say this. Let's use this language. Write the sum using sigma notation. So they might give you the expanded form and ask you for the sum. So here's our first example like that. Now, whenever I'm trying to write a sum like this using sigma notation, I know I'll have the sigma there, and then I can choose any index of summation I want. We could use any variable, but we tend to use I, J, K, sometimes L for that index of summation. Since we're going to use I a lot, I think I'm just going to stick with I. And then I want to substitute in the value of I where I start and substitute in the value of I where I stop. Those will be the lower and upper bounds of my, my sigma notation for this sum. So I write this down, I choose the value of I choose a variable to represent the index of summation, which I chose to be I. And then I look over here and I'm looking for what all of these fractions have in common. So I'm looking at this expression, this expression, this expression, all the way to that expression. I'm saying, what do they all have in common? What's the same for all of these? Well, I notice right away I have 6's in the numerators for all of those. So I'll write that down. And then I look at the denominator and I say, well, what do these have in common? Well, they have a 4 here, a 4 here, a 4 here, a 4 here. They all have 4 plus something. So I'll write the 4 down. And then I'll focus on that part that's changing. So this is a 3. I've got 4 plus 3 here, and then over here I've got 4 plus 4, and then 4 plus 5, and eventually 4 plus 13. That has to be related to my index somehow. Now we could start with I equals 1 and figure out what this would have to be in terms of I, but it's much simpler if we just start with I equals 3. Because this is a number that's increasing by 1 every time. So let's start with I equals 3 and put an I right here. So when I equals 3, we'll have 6 over 4 plus 3. That's this. If this is a sub I, if we're starting our summation with I equals 3, this will represent a sub 3. And then this must be a sub 4. And this must be a sub 5. So I think this is going to work. Now the upper index of the summation, or the upper bound of the summation, this is the index of summation, this is the lower bound, I want the upper bound. That comes from the last value of I that I substitute. Notice the last thing that we're adding to that 4 in the denominator is a 13. So that should be a 13 because this is a sub 13. So we have a sub 1, or a sub 3 plus a sub 4 plus a sub 5 all the way to a sub 13. So that's how we do that. We look at the pattern and we say, what do they have in common? Write that down. And then you want to think about what's changing and how that relates to this index. Now, if you have something that's increasing by 1 every time, like we did, we had 3, 4, 5, and so on, it's easiest to just let your index of the summation start with the first value that you see there, that 3, and then replace that 3 with an I in your a sub I over here. And then the last value that you substitute in over here, that should be your upper bound of the summation. Okay, so that's one example. Let's do another one that's similar. Say you have 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way up to 8 squared. Well, I can write that using sigma notation. Now, the first thing I want to do is think about what is staying the same. Well, for a sub I, it looks like I'm just taking an integer and squaring it. I've got something squared, something else squared, something else squared. So it's always going to be something squared. So I write that down. And then I think about what's changing. That number that we're squaring is changing. I've got 1 squared, 2 squared, 3 squared, 4 squared, and 8 squared. Now the first value of that number needs to be the first value of the index of my summation. Now you could start in a different place and write a slightly different formula here. There's infinitely many ways to write this, but we're going to try to write this in the simplest way possible. Since we start by summing a 1 squared, let's let I start with 1 and make that I squared. Well, if that's the case, then this is a sub 1 squared, or a sub 1. That would make this a sub I. So when I is 2, that's going to be a sub 2. This is a sub 3. That's a sub 4. And then over here we've got a sub 8. Since we stop at a sub 8, the upper bound of the summation needs to be 8. Okay, so now we're familiar with sigma notation. I could give you sigma notation and ask you to expand it and find the sum, or I could give you that expanded sum and ask you to write it in sigma notation. Okay, now let's talk about some properties of the summation and summation formulas. So let's say k is just a constant. It's just a real number. Then if I take the sum as I goes from 1 to n of a sub I, and each of those is multiplied by k, I can rewrite it this way. That's k times a sub 1 plus k times a sub 2 plus k times a sub 3. And we would keep going until we get to n. So I have k times a sub n. Well, isn't that the same thing as k times a sub 1 plus a sub 2 plus a sub 3 all the way through a sub n? Can't I just factor the k out from everything? Well, that's what this first property says. If you've got a constant inside the summation, you can factor it out. So this is just me explaining the property, and then I'll have the property over here. Okay, so that's one property. Now, if I'm adding a sub I and b sub I inside here, here's another property. Well, when I equals 1, I get a sub 1 plus b sub 1. When I equals 2, I get a sub 2 plus b sub 2. When I equals 3, I have a sub 3 plus b sub 3. And we keep going until we get to a sub n plus b sub n, and we stop there because the upper bound of the summation is n. Well, isn't that the same as just taking a1 plus a2 plus a3 all the way through a sub n and adding b sub 1 plus b sub 2 plus b sub 3 all the way through b sub n? Couldn't I just do that? Couldn't I grab all these a terms and put them together and then put all the b terms together? Well, I think that's perfectly legal because we can rearrange sums. We can change the order because addition is commutative. We can also change the grouping because addition is associative with real numbers. So I can do that, which means that if I'm adding two guys over here, that's the same as just taking the sum of a sub I, the sum of the a sub I, and adding it to the sum of the b sub I. Now, if I happen to be subtracting instead, then that would just make that a minus, and that would make that a minus. So whenever you see this plus or minus, that is literal. This is just shorthand for two separate rules or two separate properties. The first property is that if I have the sum as I goes from 1 to n of a sub I plus b sub I can add the a sub I and add the b sub I separately. Now the second property is that if I'm subtracting those, well, I can add the a sub I and add the b sub I and subtract those instead. Okay, so keep those properties in mind. So if k is a constant, you can factor it out. For adding those over here, it's almost like we're distributing that sigma sign. Just comes from the commutative and associative properties of the addition of real numbers. And again, the shorthand for both of these put together is just this. They'll have a sub I plus or minus b sub I. I still goes from 1 to n. Okay, so those are some properties. Now I'm going to give you some formulas. These are called summation formulas. If k is a constant, so when I equals 1, you get k. When I equals 2, you get k. When I equals 3, you get k. And you keep going. If I'm just adding k to itself every time from I equals 1 to n, this is just k n times. Because when I equals 1, I get k. When I equals 2, I get k. When I equals 3, I get k. When I equals n, I get k. And then we add them all together. So a shorthand for this is just k times n. And we did an example of that earlier. We looked at this. We said as I goes from 1 to 3, if I'm just adding 4 to itself, I get 4 plus 4 plus 4. Isn't that the same as just 4 times 3? Yeah, it sure is. That is a special case of this rule right here. Okay, here's another formula. And this one I think is really cool. When I equals 1, we get I, or excuse me, 1, I, which is 1. When I equals 2, we get 2. When I equals 3, that's just 3. And we keep going until we get to n. It turns out that that's equal to this. It's n times n plus 1 divided by 2. I'm just going to tell you a little story about this. It's a popular story. I don't actually know if it's true. And I'm sure that the version I've heard has been embellished a bit. But supposedly, here's how it goes. There's this mathematician named Gauss. He's kind of a big deal. And supposedly when he was very, very young, he had sort of a bad teacher. And the teacher is like, I need you to add up all the numbers between 1 and 100. So maybe the teacher was trying to get some work done and they had a bunch of little kids and just trying to keep them busy. So she says, go ahead, add all the numbers between 1 and 100 together. And then she goes to her office. She's trying to work on something else. And then little Gauss just knocks on the door. And she's like, yes. And he's like, I guess his name is Carl. She's like, yes, Carl. And he's like, oh, then the sum of all the numbers between 1 and 100 is 5,050. And she's like, why don't you add up all the numbers between 1 and 1,000? And so she sends him back to the room to do that. And then like a few minutes later, here's little Carl Gauss comes to her door. And he's like, oh, I already know the answer to that too. And the reason that he was able to add all the numbers between 1 and 100 quickly, or between 1 and 1,000 quickly, is because he recognized this formula right here. If you're wondering, like, how did little 6-year-old Gauss do this? Like, how is that even possible? This is supposedly what he did. So this Gauss's teacher says, add all the numbers between 1 and 100. So 1 plus 2 plus 3. Talk about busy work, right? So supposedly Gauss said, okay, well, I could do that. I could also take that and add all the numbers between 1 and 100, but backwards this time. So I'll have 100, and then 99, and 98, and 97. And eventually I'll have a 1 over here, and a 2 over here, and a 3 over here, a 4 here, and a 5 here. So Gauss said, let's put all the numbers between 1 and 100 that way, and then let's put them here backwards. And then look what happens. In columns, we've got 1 plus 100 is 101. And then 2 plus 99, hey, that's 101. And 3 plus 98 is 101. We always get 101 in these columns. So I've got 101 of these. I've got 101 there, 101 there, 101 there, 101 there. And what is this? This is the same as 2 times the sum he's looking for. So he said, well, what is the sum of all the numbers between 1 and 100? Well, I guess what I could do is I could write it twice. I could add them together. I get 101. And say, well, how many times do we have 101 right there? I think we have it 100 times. So it's 100 times 101. But that's not actually the sum I'm looking for. That's twice that, because I have the sum from 1 to 100 there and the sum from 1 to 100 there. So divide it by 2. And that's 50 times 101, which happens to be 5,050. That's how he did it fast. You're saying, what does that have to do with anything? Well, in general, that's the shortcut. If I take all the numbers between 1 and n, and then I add them in this direction and in this direction, and then I add in columns, well, I'm going to have n columns, and in each column, the sum is n plus 1, just like we had here. N was 100, so I've got 100 columns, and in each column, the sum is 101, but that's going to be twice what I need, so I need to divide it by 2. So he says, you've got n columns. In each column, the sum is 100, or n plus 1. Take that and divide by 2, and that's the sum of all the numbers between 1 and n. So that's what Gauss supposedly did. Thought that was a cute little story. Who knows if it's true? Yeah, that is how that summation formula came about. Supposedly. I'm sure it's exaggerated a little. Okay. But Gauss did come up with it. So if you add 1 plus 2 plus 3 all the way up to 100, it turns out you're going to get 100 times 101 divided by 2. If you wanted to add all the numbers between 1 and 1,000, you'd have 1,000 times 1,001 divided by 2. That's how you do it. That's the shortcut. Now I don't have the shortcut for this, but the sum of the I squared is a common one as well. When I equals 1, we get 1 squared. When I equals 2, we get 2 squared. I equals 3, we get 3 squared. Eventually, we're going to get to n squared, and we'll stop. It turns out that this is equal to this. It's n times n plus 1 times 2n plus 1, all divided by 6. If you're thinking, what on earth? I know. But it turns out that's what you get. So 1 plus 4 plus 9, all the way up to 100 squared, turns out to be 100 times 101 times 201 divided by 6. That's what you get. And of course, you can plug in other values for n as well. Another one that may come up for us is the sum as I goes from 1 to n of I cubed. So that's 1 cubed plus 2 cubed plus 3 cubed, all the way up to n cubed. This is pretty cool. Turns out that you just get this squared. So the sum as I goes from 1 to n of I cubed is actually the sum of the i's squared. So you have n times n plus 1 over 2, and you square it. There's some very pretty visual proofs of this stuff if you Google it. square each of the factors separately. There's that book, I think I may have mentioned it to you guys earlier this semester, called Proof Without Words. Show you all these pretty pictures, and the pictures will show you how this is related to that and how this is related to that squared. And I think it's pretty cool. Okay, so those are 4 summation formulas that we're going to take for granted. I showed you where that came from. I think we all understand where that came from. These I didn't prove to you, I just told them to you. But if you Google summation formulas and maybe proof without words, I think you should be able to see some visual proofs of this that show you why adding all those squares together in this way should be, we should be able to simplify it by just doing this times this over 6. Okay, so now we're going to use these summation formulas to write sums without sigma notation. So if I have something in sigma notation that looks like this, well, I can rewrite it like this. Now, if I have a constant in front of my I, well, according to this, I can factor out the constant. And if I have a sum of 2 terms, well, I can just do the sum of the a sub I and then add the sum of the b sub I. If I'm subtracting like this, well, I can just do the sum of the a sub I minus the sum of the b sub I. So we're going to use all of these properties and these summation formulas to write summations without sigma notation now. And this is, again, getting ready, getting us prepared to find the area under a curve using sums of areas of rectangles, which we'll look at in the next video. Okay, so let's say somebody asks you to use summation formulas to write the sum without sigma notation. And then we want to find the sum for different values of n, for n equals 10, n equals 100, n equals 1,000, and n equals 10,000. Okay, so here's our example. We have the sum as I goes from 1 to n of 3i times I minus 1 all over n cubed. Now, n is just a counter. As far as we are concerned, when I'm looking at this, even though it looks like n is a variable, it's not. It just tells you where to stop counting. This I, that's the index of the summation, that changes from term to term. So this says start at I equals 1. So when I equals 1, we'll get 3 times 1 minus 1 over n cubed. When I equals 2, we'll get 3 times I, which is 2, times I, or 2 minus 1 over n cubed, and so on. You just keep going like this. And eventually you're going to stop at I equals n. You don't have to write this out this way in order to use the summation formulas, but I wanted to just to remind you of what this looks like. When I equals 1, we have 3 times 1 times 1 minus 1 over n cubed. So we turn out to get 0 there. When I equals 2, we get 3 times 2 times 2 minus 1 over n cubed. Just replacing the i's with 2's. Now replace the i's with 3's. We'll have 3 times 3 minus 1 over n cubed. And then the last one, you replace the I with n. So we'll have 3 times n minus 1 over n cubed. And the question is, how can I write this without sigma notation? Well, I've got summation formulas and a couple of properties. You can think of that as 2 properties, or you can think of this property as 2 separate properties, 3 properties. But we can use these formulas to rewrite this guy without the summation. Okay, so notice here that n cubed, that n is just being treated as a constant in each of these. Since n is a constant, we can factor that out. So I'll start by factoring out my 1 over n cubed, because that's an n cubed in the denominator. And I think I want to distribute that 3i as well. So we'll have 3i squared minus 3i and actually I think I want to take the 3 out as well, because 3 is a constant. So we can factor the 3 out of the summation. So I've got 3 over n cubed. Oops. And now I've got an I squared minus I in this summation. Now because I've got an a sub I minus a b sub I here, I'm going to write this as a difference of two different summations. So I still have that 3 over n cubed multiplying everything, but I'm going to think of this as the sum as I goes from 1 to n of I squared minus the sum as I goes from 1 to n of I. So I have simplified this as much as possible until I get something that I have a formula for and something that I have a formula for. I've got a formula for the i's and I've got a formula for the I squareds. So now we substitute. The sum of the i's as I goes from 1 to n is n times n plus 1 over 2. Thank you, Gauss. Gauss came up with that when he was a little kid. And the sum of the I squared as I goes from 1 to n is n times n plus 1 times 2n plus 1 over 6. So we're substituting both of those. So this I squared can be rewritten this way, according to this formula. It's replaced by n times n plus 1 times 2n plus 1, all divided by 6. And then we're subtracting what we get here, which is n times n plus 1 over 2. Now you can leave this way if you want to, or you could distribute that 3 over n cubed to everything. I think I'll distribute. So I've got 3n times n plus 1 times 2n plus 1 over 6n cubed. And then I'm distributing that to this term and to this term. So we'll have minus 3 times n plus 1 over 2 times n cubed. Simplify where you can. 3 goes into 6 twice. N goes into n cubed once, so we can factor out that n. So we'll be left with an n squared down here. That n goes into that. And we can reduce one of those n's, so we have an n squared down there. So I've got a 2n squared in this denominator and a 2n squared in that denominator. So this can be simplified this way. I've got n plus 1 times 2n plus 1 minus 3 times the quantity n plus 1, all divided by 2n squared. And you could start substituting. We were asked to find the sum for n equals 10, 100, 1,000, and 10,000. I think I'd still like to simplify a little further. It's not necessary, but I think I'd like everything would look nicer if it was just a little bit simpler. So I look at this, and I see that they have an n plus 1 in common. So we factor out the n plus 1. And then what's left over is I take n plus 1 and I'm multiplying by 2n plus 1. Oops. So that times that gives me the first term, and n plus 1 times a negative 3 gives me the second term. And that simplifies quite nicely. I have n plus 1, and 2n, 1 minus 3 is 2. So that's negative 2, excuse me. We even get one more cancellation. Factor out the 2 from that. And the 2's reduce, and you get this. So you can use this if you want to. N plus 1 times n minus 1 over n squared, or you could write that as n squared minus 1 over n squared. Or you could write that as 1 minus 1 over n squared, doing this over this, minus 1 over that. Either one is the simplified version. Okay, so now we were asked to write this without summations. And we actually had achieved our goal when we got here. We just simplified it. This, through algebraic manipulation, can be shown to be equal to these. For a test or a quiz, as far as I'm concerned, this would be fine, but these are the answers that you're going to tend to see in the back of the book, something simplified. So we wrote it without the summation notation. Notice that when we substitute, that sigma is gone. This is the sum of the I squareds as I goes from 1 to n. That happens to be this number. So we substitute that, the sigma is no longer there. Okay, so now we've got this. We're asked to evaluate this for n equals 10, n equals 100, n equals 1,000, and n equals 10,000. So we'll have, I think I'll use this version, 1 minus 1 over 10 squared, 1 minus 1 over 100 squared, 1 minus 1 over 1,000 squared, and 1 minus 1 over 10,000 squared. Well, 1 minus 1/100th is 0.99, we know that. So I get 99 over 100. And then I'll have 1 minus 1 over 100 squared. So that's 4 zeros. So 0.9999. Now if I have 6 zeros, 1 minus 1 over 1, 1, 2, 3, 4, 5, 6. What's that, a million? 1 millionth? Now we've got 6 nines here. And we're going to have 8 zeros. That means we're going to have 8 nines over here. Okay. What's happening to this expression as n goes to infinity? That's another important question that it's related to finding that area under a curve. If I'm looking at this and I'm thinking about what happens as n goes to infinity, this is an infinity over infinity indeterminate form. But if I divide this by n squared and I divide that by n squared, that's not indeterminate. As n goes to infinity, this expression approaches 0, and so we get 1. And we can see when n is 10, when n is 100, when n is 1,000, when n is 10,000, we're getting closer and closer to 1. We're adding more and more nines there. If we could have infinitely many nines, turns out that that's actually equal to 1. Okay, so that is our summation formula. And that is the end of our lesson on sigma notation. So brief review. This is sigma notation. These are called the terms of the summation. I or J or K or whatever that letter is there, that's called the index of the summation. This number in front of the sigma sign, that's called the ith term of the summation. Or if there was a J, that would be the jth term. If there's a K, that'd be the kth term. The number where you start, that's in the bottom, that's the lower bound of summation. It's the first number the first value of the index that you plug in. This number up here is called the upper bound of the summation. That's where you stop adding. We can take a summation and expand it and simplify. Sometimes we're given an expanded summation and we're asked to write it in sigma notation. And then we've got all these properties that will allow us to write something that's given in sigma notation without sigma notation, like we did on this one. So usually it's factoring out constants. If you have a sum or difference of terms using this property here. And then once you get to this point where you start to see something from your summation formulas, then you just substitute. This gets replaced with this. This gets replaced with this. Then that's your answer. That's what that expression is without any ends in it. But then we want to simplify. So we do a bunch of algebra. We simplify here. And then if somebody asks you, what's the value of that sum when n equals 10, 100, 1,000, 10,000? You just plug in that value of n to your simplified answer. And often we're interested in what happens to that summation as n goes to infinity. So even though we weren't asked for it this time, we computed that limit. It turns out that this gets closer and closer to 1 as n goes to infinity. We'll see that that is related to the area under the curve in the next video.